Now let's see the solutions. For oscillations, there should be at least two energy storing elements in the network. In other words, we can say that the order must be at least 2. So the first option is true. As given in the question, the step response has oscillations which dies out after some time, and this is possible only when we have a complex conjugate pole pair. In other words, the system is underdamped. If the poles are not conjugate pair and are lying exactly over the axis, either real axis or imaginary axis, then there is no chance we will get oscillations which dies out. If the poles are lying on the imaginary axis, the output will have oscillations but they will not die out. Now let's see the next question. We can find a transfer function of a differentiator which will come out to be equal to k multiplied by Laplace variable s, where k is a constant. A differentiator usually acts as a high-pass filter. All these filters are particularly used for sinusoidal signals only. So here you have to assume sinusoidal input signals by answering the question. The transfer function, we have to ignore the damping factor, and afterward you can see that the magnitude increases linearly with frequency. Now let's come to the next question. We are aware that the pose of a standard second order control system is in the form of minus zeta into natural frequency omega n plus minus j omega n multiplied by under root of 1 minus zeta square. After comparing it with the pose which are provided in the question, we will get the value of natural frequency multiplied by 1 minus zeta square to be equal to 4. Now we know the formula for peak time is equal to pi divided by natural frequency multiplied by under root of 1 minus zeta square. After putting the value, you will get the peak time to be approximately equal to 0.785 second. Now let's come to the next question. We already know that the output of sinusoidal inputs is of the form A multiplied by sine t plus theta, where A is the magnitude of the transfer function which simply gets multiplied by the input signal. Similarly, theta is the phase shift which is provided by the transfer function and gets added directly to the input signal. The amplitude and phase can easily be found, which will come out to be equal to 1 by root 2 and minus pi by 4. By putting these values, you will get the steady state output is equal to 1 by root 2 multiplied by sine t minus pi by 4, and hence the first option is correct. Now let's see the last question. We can easily find the transfer function of the provided system, which will come out to be equal to k divided by tau s plus k plus 1. We know the Laplace transform of the output function is equal to the transfer function multiplied by the Laplace transform of the input function. After that, we can find the steady state value of the output, which will come out to be equal to tan k divided by k plus 1. From the output profile, we can clearly say that the steady state value of the output is actually equal to 8. By equating 8 equal to tan k divided by k plus 1, we can find the value of k, which will come out to be equal to 4.